Hi, my name is Erin, and this is my presentation. My major is computer science, and this presentation has to do with how linear algebra is related to my major, computer science.
Computer science depends on linear algebra in lots of ways. Linear algebra provides the skills to know how to manipulate data stored in your program. Computer science deals with arrays of all sizes to store and manipulate information. Here, in computer science, we call those one-dimensional arrays and two-dimensional arrays, while in linear algebra, we call them vectors and matrices. More specifically, linear algebra helps with image processing and 3D graphics in computer science. Creating images in computer science involves displaying and manipulating values through arrays or matrices in two-dimensional plots or three-dimensional plots. Most images are represented through these matrices, which must be transformed to create the next image or adapt to the environment created around them. Transforming an image involves changing the values within the matrices that represent the image you wish to alter. Processing and rendering these images within a program is all dependent on skills learned in linear algebra. Changing these matrices is known as linear transformations. There's lots of different types of transformations. There's reflection, rotation, shearing, squeezing, stretching, translation, and orthogonal projection. On the next slide, I will give you an example of orthogonal projection. Here is an example of orthogonal projection. Finding the orthogonal projection of y onto u, we have a vector of 7 and 1 and a u vector of 3 and 2. There is an initial equation that goes with orthogonal projection, and it's y dot u divided by u dot u times multiplied by the matrix of u. Y dot u, that's 7 times 4 plus 1 times 2, that would equal 30, and u dot u, that's 3 times 3 plus 2 times 2, which would equal 13. Plugging those numbers back into the equation, and you would get 30 over 13 multiplied by the u vector 3, 2. And then you see on the circled answer towards the bottom right, and that's how you get your orthogonal projection of y onto u.